In 1941, the United States Navy had a problem. They needed shelters, thousands of them, fast. Shelters that could survive typhoons in the Pacific, blizzards in the Arctic, and bombing raids in Europe. They needed structures that untrained troops could assemble in hours with hand tools on a beach. So they built them, 170,000 of them. Steel arch shelters, curved panels bolted to a concrete slab, no internal frame, no skilled labor required. The design was so effective that by the end of World War II, these shelters had served as barracks, hospitals, command posts, aircraft hangars, and ammunition storage across every theater of the war. Today, you can build one for $300. FEMA will not certify it. No federal preparedness document mentions it. Or the only storm shelters that qualify for government grant funding start at $10,000 and run north of $50,000. The $300 design that the U.S. military mass-produced for wartime, it doesn't appear in a single official recommendation. By the end of this video, you will know exactly how to build a steel arch emergency shelter from materials you can buy at any building supply store. You will understand why it works structurally, and you will understand why no official source will ever tell you about it. Try to crush an egg end to end, squeeze it between your palms with the force directed through the tips. You can't do it. That compression principle is the engineering foundation of everything you are about to learn. To understand why this works and why you have never been told about it, we need to go back to 1941. This channel exists because the gap between what actually works and what is officially recommended keeps getting wider every year. Practical knowledge that used to be common, knowledge that kept families alive through disasters and depressions and wars, has been quietly replaced by expensive commercial products and bureaucratic certification systems that serve manufacturers more than they serve you. If you are new here, this is what we do. We recover that knowledge, we verify it against modern engineering and science, and we hand it to you in a format you can actually use. If that sounds like something you need, subscribe. You are joining a community that prioritizes practical, affordable preparedness over commercial dependency. Now let me tell you where this shelter came from and why the story matters. January 1941, Quonset Point Naval Air Station, North Kingstown, Rhode Island. The Navy contracts the George A. Fuller Company, one of the largest construction firms in America, to design a lightweight, portable, rapidly deployable shelter for military operations worldwide. The design requirements were brutal. It had to ship flat. It had to survive extreme weather on 6 continents. It had to be assembled by men with no construction experience using basic hand tools. And it had to be cheap enough to produce by the tens of thousands under wartime material rationing. Fuller's engineers looked at the problem and arrived at the same answer that Roman architects discovered 2,000 years earlier, the arch. They designed a semicircular structure made from curved corrugated steel panels bolted to a concrete or wooden foundation. No internal frame. The curved skin itself carried all the structural loads. The design was designated the Quonset hut, named after the point where it was born. Production began immediately, and the scale was staggering. The United States Navy construction battalions, the Seabees, deployed Quonset huts across the Pacific Theater. Island beaches with no infrastructure, tropical storms that flattened conventional tents and wooden structures. The arched steel shells stayed standing. They went to Europe, they went to North Africa, they went to Arctic staging areas in Alaska and Greenland, where temperatures dropped to 40 degrees below 0 Fahrenheit, and winds exceeded 100 miles per hour. 170,000 units, every theater of operations, assembled by troops who were welders and farmers and clerks 3 months earlier, on beaches, in mud, on frozen ground, with hand tools, in hours. When the war ended, thousands of surplus Quonset huts were sold to civilians. Entire neighborhoods sprang up near former military bases. Families lived in them. Businesses operated out of them. Churches held services in them. Some of those structures are still standing today, over 80 years later. The military built 170,000 of these because they worked under the worst conditions on Earth. The question is, why can you not build one in your backyard today? Now, everything you need to build this shelter is in this video. Every measurement, every material, every step. But if you want to go deeper, the vault has what the video cannot fit. Detailed material sourcing lists broken down by region, supplier contacts for bulk corrugated steel, foundation engineering tables for different soil types, from sandy coastal soil to heavy clay. Regional building code navigation strategies, so you know exactly what your county requires before you pour a single yard of concrete. The vault is reference material for people who are actually going to build. No filler, no padding. But stay right here, because what comes next changes how you understand every house you have ever lived in. Let me show you exactly why a curved steel shell survives winds that turn a conventional home into a debris field. Your house, if it is like most American houses, is a wooden frame covered in flat panels, plywood sheathing, drywall interior, flat roof planes or low-pitched gables, flat walls standing vertical to the ground. Here is what happens to that house in a Category 5 hurricane. Winds exceeding 157 miles per hour. Wind hits the flat windward wall. Pressure builds against that surface. Simultaneously, wind accelerating over the roof creates a low-pressure zone above, exactly the same principle that lifts an airplane wing. The house now has high pressure pushing inward on the walls and low pressure pulling upward on the roof. The weakest point is the roof-to-wall connection. Metal clips, sometimes just toe-nailed rafters. That connection fails. The roof lifts. The moment the roof separates, the walls lose their lateral bracing. They fold. The house is gone. This is not speculation. This is the documented failure sequence of wood frame construction in every major hurricane study conducted since Hurricane Andrew in 1992. Now consider the arch. Wind hits a curved surface. There is no flat plane to catch. The airstream divides and flows over the curve the same way water flows around a river stone. Pressure does not concentrate. It distributes. The force that does contact the shell converts into compression along the curve, not bending. Compression. The arch pushes downward into its foundation at both base points. The entire structure is being squeezed together, not pulled apart. This is why the egg does not break. Force applied through the arch converts to compression, and steel in compression is extraordinarily strong. Now add corrugation. A flat sheet of 26-gauge steel is flimsy. You can bend it with your hands, but corrugate that same sheet, add those parallel ridges, and something remarkable happens. The moment of inertia increases dramatically. That is an engineering term that means resistance to bending relative to weight. The ridges turn a floppy sheet into a rigid beam. The technical term for this type of structure is monocoque. The skin is the structure. There is no internal frame to fail because the curved, corrugated skin carries all loads simultaneously. Aircraft fuselages use this principle. Eggshells use this principle. The Quonset hut uses this principle. The critical insight is aerodynamic uplift. That same low-pressure effect that rips roofs off houses also pulls upward on an arch. If the arch is not anchored to its foundation, it becomes a sail. Anchoring is everything. Remember that. It matters more than anything else I will tell you today. So the engineering is proven. The military validated it 170,000 times. The question becomes, if this design is so effective and so cheap, why does FEMA not tell you about it? Here's where the story gets uncomfortable. FEMA publishes 2 key documents for storm shelter construction. Publication P320, titled Taking Shelter from the Storm, and Publication P361, Design and Construction Guidance for Community Safe Rooms. These are the federal standards. To be certified as a FEMA-compliant safe room, a structure must meet specific debris impact criteria. For tornado zones, the structure must withstand a 15-pound 2x4 lumber missile traveling at 100 miles per hour. For hurricane zones, a 9-pound missile at various speeds depending on wind zone classification, the structure must resist wind loads of 250 miles per hour, and every design must bear the stamp of a licensed professional engineer. That professional engineer stamp is the gate. A PE stamp design requires engineering analysis specific to the site, the soil conditions, the wind zone, and the exact materials used. That costs thousands of dollars before a single panel is purchased. FEMA's Hazard Mitigation Grant Program will cover up to 75% of the cost of a certified safe room. That sounds generous. But only certified safe rooms qualify. A do-it-yourself steel arch shelter built from commodity materials does not qualify regardless of its structural performance. The commercial alternatives that do qualify? Steelmaster buildings. Curvco steel structures. American Steel Span. These are professionally engineered, commercially manufactured steel arch buildings. They start at $10,000. Complex configurations run to $50,000 and beyond. Here's the outcome the system produces. The cheapest, most historically proven shelter design in American military history is invisible in official guidance. The only endorsed options cost 20 to 100 times more. And the people most likely to die in tornadoes and hurricanes, low-income families living in mobile homes and older wood frame houses, are precisely the people who cannot afford the only shelters the government endorses. I want to be precise about what I'm saying here. I am not claiming a conspiracy in a back room. I am saying the regulatory structure produces a convenient outcome for commercial manufacturers and an inconvenient outcome for vulnerable families. The testing criteria are legitimate safety standards. The engineering stamp requirement exists for real liability reasons, but the result is that a $300 shelter with 80 years of military validation does not exist in any federal document, while $10,000 commercial products enjoy taxpayer-funded grants. That is not banned. That is regulated out of practical existence. And you should understand the difference. If you're the kind of person who would rather spend $300 on steel than $50,000 on a commercial safe room, this channel is built for you. Subscribe so you do not miss what comes next. We cover practical, affordable solutions that institutions have no financial incentive to promote. Now, I need to be honest with you about what this shelter can and cannot do. A do-it-yourself steel arch shelter built from 26-gauge corrugated panels has not been tested against FEMA P361 missile impact criteria in this specific configuration. I cannot tell you it will stop a 15-pound 2x4 traveling at 100 miles per hour. It might. Corrugated steel is substantially more resistant to puncture than plywood or vinyl siding. But I do not have test data, and I will not fabricate a claim. Thermal performance without insulation is poor. Steel conducts heat rapidly. In summer, an uninsulated steel arch is an oven. In winter, it is a refrigerator. Condensation on interior surfaces creates moisture problems. Long-term corrosion requires maintenance, specifically elastomeric coatings and regular inspection. This is not a nuclear shelter, not a chemical or biological shelter, not a flood shelter. A steel arch provides wind and structural collapse protection. Period. If your area floods, elevation and waterproofing are separate problems entirely. An all-metal structure requires lightning grounding. Without a proper ground rod and bonding conductor, you are sitting inside a lightning collector. And here is the single most critical limitation. If the anchoring fails, this shelter does not just stop protecting you, it becomes a projectile. A steel arch that separates from its foundation in high winds is a massive, tumbling piece of metal. Anchoring is not optional. It is not a suggestion. It is the difference between a shelter and a weapon. I'm not telling you this is a certified safe room. It is not. What it is, a structure that is almost certainly stronger than the wood frame house you're currently depending on to survive a Category 4 hurricane. The question is not whether this is perfect. The question is whether it is better than crouching in an interior closet with a mattress over your head. Here's how you build it. Step 1. Site selection. Choose level ground with good drainage, away from large trees that could fall on the structure. Avoid low-lying areas that collect water. Step 2. Foundation. Pour a concrete slab at least 4 inches thick, reinforced with wire mesh or number 3 rebar on 12-inch centers. The slab should be 8 to 10 feet wide and 12 to 16 feet long. That footprint shelters a family of 4 with supply storage space. Step 3. Anchor bolts. Before the concrete cures, set J-bolts or plan for post-cure wedge anchors spaced every 24 to 36 inches along both long edges of the slab. These anchors are the most critical component of the entire structure. Use half-inch diameter minimum. Embed J-bolts at least 3 inches into the concrete. Step 4. Panel selection. Purchase 26-gauge corrugated galvanized steel panels. For higher wind zones or larger spans, use 24-gauge. Standard panels come in 2-foot and 3-foot widths in various lengths. You need enough panels to create arches spanning the width of your slab. Step 5. Bending the arch. For an 8-foot wide slab, each arch panel needs an approximate circumference of 12.5 feet. Panels can be bent gradually using a simple roller setup or by hand over a curved form. The radius must be consistent. Uneven curves create stress concentration points. Step 6. Assembly. Start at one end of the slab. Set the first arch panel with its base flanges aligned over the anchor bolts on both sides. Secure with nuts and washers. Add subsequent arch panels overlapping by 1 to 2 corrugations. Fasten panels to each other every 6 to 12 inches along the seams using self-drilling Tech screws or bolts with neoprene washers. Step 7. End walls. Frame both ends using steel angle iron, steel square tubing, or heavy treated lumber. One end gets a door. Size the door for rapid entry during an emergency, at least 32 inches wide. The other end can be solid or include a small ventilation opening with a closable cover. On Step 8. Sealing. Apply butyl tape or polyurethane sealant on all panel seams before final fastening. After assembly, coat the entire exterior with elastomeric roof coating. This prevents water infiltration and dramatically slows corrosion. Step 9. Grounding. Drive an 8-foot copper-clad ground rod within 2 feet of the structure. Bond it to the steel shell with a number 6 copper conductor and proper ground clamp. Step 10. Interior preparation. Stock the shelter with a minimum of 1 gallon of water per person per day for 3 days. Non-perishable food, a comprehensive first aid kit, a battery-powered or hand-crank weather radio, blankets, sanitation supplies, including a 5-gallon bucket with plastic bags and cat litter. Secure all storage to the walls or floor so nothing becomes a projectile during high winds. Total material cost for the shelter structure, $300 to $500, depending on steel prices in your region and whether you use 26-gauge or 24-gauge panels. Let me put this in perspective. In 1941, the United States Navy looked at the most hostile environments on the planet and chose a corrugated steel arch as the solution. Not because it was elegant, because it worked. They built 170,000 of them. They sheltered soldiers in typhoons across the Pacific. They survived Arctic winds that would shatter a conventional building. The engineering has not changed. Arches still distribute load into compression. Corrugated steel still resists bending far beyond what its weight suggests. Monocoque shells still outperform framed structures in extreme wind loading. What has changed is who profits from your need for protection. $300 in steel and concrete. That is the cost of a shelter. The United States Navy built 170,000 of FEMA's approved alternative starts at $10,000. The people who need shelters most, families in mobile homes in Tornado Alley, families in older houses on the Gulf Coast, cannot afford $10,000. They can afford $300. No institution has a financial incentive to tell you what I just told you. You cannot patent an arch. You cannot trademark corrugated steel. You cannot create a subscription model around a concrete slab and some bolts. There is no recurring revenue in a $300 shelter that lasts 80 years. Well, you now know how to build something the United States military trusted with soldiers' lives for less than what most people spend on a weekend. The engineering is public domain. The materials are at your local building supply store. The knowledge is now in your hands. Someone you know lives in a mobile home in a hurricane zone. Someone you know cannot afford a $10,000 safe room. Send them this video. That might be the most important thing you do with the next 30 seconds. Next week, we are going deep on water. Specifically, a filtration method that was standard military field equipment for decades and costs less than $20 to build. The commercial equivalent sells for $200. Same pattern, same players, same silence. If you're not subscribed, now is the time. We will see you next week.